talk is about Human-Centric Machine-Learning by Matthias Gallet. And so artificial intelligence can be very effective to come up with a good solution for rather difficult problems. However, if the goal is not very well defined, the result can be unexpected. So as you probably know, humans are sometimes not really that good at explaining what they really want. And so in this talk, we'll be focusing especially on the NLP aspects of this topic. So please join me in welcoming Mr. Gallet.
Thank you very much. And thanks a lot for the invitation. So I work in France, so Naval Labs Europe is located in Grenoble, in the southern France. And it used to be a research center which belonged to Xerox Research. It got acquired 3 months ago officially by Naver, which is a Korean company, which owns Line, which I understand is very popular here in Japan. So what I'm going to talk about is this title, Human-Centric Machine-Learning. I kind of chose a topic which I thought would go with the audience, and it's about deploying machine learning systems in real world and some pitfalls that you should avoid, and things which you might not find in academic papers, but I think most of you will agree with some of these things. And as was said, most of the examples I will show to illustrate this is NLP for natural language processing, because well, so my background, I did the NLP team in Grenoble. So a pop quiz question, do you know who this person is?
Yes.
That's good. The chess piece is betrayed him. So this video here, which I hope will work, shows, this is almost exactly 20 years ago, March 97. So I think you know this. This was a very, I remember this, right? I was pretty young at the time, but I remember this. And especially in the Western culture, it was a very, very important milestone. I think it's similar to what happened with Go over here. And chess was seen as a pinnacle of human intelligence. So Kasparov was seen as the pinnacle of human intelligence because he was the best, he's still the best chess player in the world. And here's the moment when he realized that he had looks, right? And his face, the resolution is very bad, but the face is astonishing. Now, Kasparov, being who is a very remarkable person, he didn't stop there, right? So I think you know this. A few months later, so it was beginning of 98, he organized the first event of something which is called advanced chess. And I couldn't find a nice license-free images, but you can Google it and you will see the way it works that you have humans playing, but each human can be helped by a computer. So it is a combination of both things, that the human gives the overall strategy where the human wants to go, and then the computer basically helps him proposing different strategies together. And here also published this book here, that's written since last year or this year, and this is a combination of where machine intelligence ends and human creativity begins. So I want to keep this in mind because I will come back to these things, that these things are not exclusive. So I tried to keep the technical details at a minimum, but let me talk a bit about some formulas. So we will start with a big branch of machine learning. I think the most popular today is called supervised learning. I guess most of you are familiar with these things. So the way this works is that you have a human who takes a data set which is X, and then this is a collection of data points, images, time logs, text, documents, whatever, dialogues, and annotates them with some structured or non-structured labels Y. So we'll keep it simple, we'll just assume it's a classification problem. You have text documents, you want to label them to which class it belongs. It gives this set to the machine. The human machine makes its computation. It spits out a function f, which can take unseen data points x and produces a label which should be the one that the human has set is the corresponding label here. And then this f has to have a few characteristics. And the most general one is what's called empirical risk minimization. So what you want to minimize this expression here. And the most important part here is the L function, the loss function here, which tries to match what your function says about the x. It tries to compute the distance between what the function says is should x be and what x really is, which is a y. And this loss function measures the distance. You have a regularization here, which we want to talk about, but you see, so you're trying, that's because it's called empirical risk minimization. And something which I think is very peculiar to machine learning is that the way that this loss function is defined. So in the in the most pure sense, what you would like to have, something that's called the 0-1 loss, which says you get penalized by 1 every time your f of x is different from y, and you get 0, so you don't get penalized if it's fine. Okay, that's what you really want. Now, minimizing or optimizing the 0-1 loss is what's called an hard problem. It's untractable. So what a theoretical computer scientist would do in this case would say, okay, let's produce algorithms who are approximated, or let's produce subclasses where it gets solved exactly, and let's characterize these subclasses. What machine learning people do is a very pragmatic approach to say, screw 0-1, forget the 0-1 loss. Try to find another one which is kind of similar, which makes good sense, and which is easy to minimize. So this very pragmatic approach, I think, is behind many of the successes of machine learning, but also poses a few risks, and that's the point of this talk. So supervised learning is great if you know what you want, and if you can formalize it, which is not necessarily the same things. Formalize it under some way of formula. And of course, and that's not minor, you have to have time, money, and data to annotate these things. And remember, these things are very, very domain-specific for the moment. And so if you train it for one thing and you change domain, you may have to retrain it. Big topic in machine learning. So let me talk about an example and say why these things might be hard to formalize. So I understand that people here may be interested in machine translation, something we have looked a lot in the past and we're looking again now. And the problem of machine translation, when you want to evaluate, is that you have a proposed translation P here, and you have one of possible many target goal translation C. And the question is, how far away is this P of your T? Okay, so what you want to say is are they semantically equivalent? Now, if you could solve this specific problem, which is called paraphrasing, you have solved lots of NLP. Okay, it's what's sometimes called an NLP hard problem. Okay, so it's core to NLP. And so solving this equivalent problem is hard by itself. So what people do is they get a pragmatic approach. They try to do something simpler. And the standard way for many years, changing now, but it's still the standard, is what's called the bleu score. I don't go into the details, but basically you look at n-gram sequences of words in your NP, and you see how many of them are contained in T. If all of them are, then you're fine. If not, it's bad. It's a variation, but roughly it's this thing. Now the problem with bleu score is that it is not necessarily aligned with what humans think is a good translation. So what you can see here is bleu score on the x-axis, y score on the human score on the y-axis, and human scores these systems on two levels, adequacy and fluency, which are different. And what you can see here is that if you would look only at the bleu score, then this phrase-based system, I think it's Moses-based, seems to perform better than this company. So this Citron is a French, now Korean company. It performs better, but actually humans think that this one here performs better. Okay? So now we have a situation where you have one of the holy grails of NLP. The way that you evaluate it does not necessarily correspond how humans evaluate it. So what happens if you are in this situation? So there are at least two consequences. I think these are the same consequences that will apply to everybody who pushes something out which does very well on her academic scores, but which do not necessarily capture human ones. And so two of these consequences, at least two of these consequences, I see these two here. The first one is that people won't use your system. And you and me, we use Google Translate or Papa, which is the neighbor equivalent of these things, to get the gist of what is behind some text. But real translation, if you want to apply to members or something like this, you can't rely on these things. They need real translators. The way that real translation works since years now is with this framework called computer-assisted translation. You have a first pass by the machine, and then you want to modify it afterwards. For many years, these companies, they used rule-based systems. The reason being that the errors that the rule-based systems made were more consistent, were easier for the humans to recognize and to correct, and often were also better. Okay? And so they start to use now phrase-based or even neural-based machine translation, but for many years it didn't. A second problem you will have is you will start to having lots of different problems you have to solve, which are not intrinsic to your problem. So two of these things are in machine translation, quality prediction, something that we in the lab did for many years, 10 years ago. And the problem of quality prediction is I give you a text, I give you a translation, and now you have to tell me how good this translation is. Now, if your model would be good, then you would just take the probability of the model, which is normally output together with the translation, and this would be a good measure. This is not a good measure, as we saw, right? So you need another model to tell you how good the translation is. And the second one is this big trend in MT right now. It was a shared task on this in ACL last year. It's automatic post-edition, so it's basically what the humans did here, but in an automatic way. So you have your translation model, and now you have another model which basically tries to correct the errors that you first modeled it. Again, in theory, you shouldn't have these kind of problems if you would be able to formulate correctly the problem from the beginning. Let me go to a second part where we will see similar problems. So the second big family of machine learning is unsupervised learning. Here you don't have a human at the beginning, you have a human at the end. So the machine here eats lots of unlabeled data, you don't have any labels here. And it tries to figure out some patterns. So it produces some partition function, which can then be passed on to the human to analyze these things. So this Z, it depends on the application. Clustering is a canonical example here. LDA, if this rings a bell for you. So this set of Z captures some kind of prior about how well you want to minimize this, you want to play Occam's razor, for instance, how much you want to cover the whole data. So it varies a bit on application, but the idea is it is some way of formalizing the prior that you have. And people use this, in theory, if they have a corpus. They don't really know what they want of this corpus, they just want to understand it better. But they assume that there are some patterns, there's something inside the original corpus. Now again, in real life, these two things don't necessarily happen, or it doesn't always happen that you don't know anything about the corpus. What happens most of the cases is, in applications, is something more related to this, what we call exploratory search. This term of exploratory search captures all instances where you start digging into your data. You don't really know what it is that you're looking for, but you have an abstract definition which might be over-specified, or it might be multifaceted, meaning that you're looking for some relevant documents, but they might be relevant for several reasons, not only for one. And while you are looking into this information, and if everybody who did a literature review now how this works, while you start reading, you understand better, and it guides your search to one direction or another. So the best way I found to summarize this is with this expression, I know it when I see it. And as it happens, it's actually a real expression coined by, or famous, because in the 60s a US judge talked about this. In this case, it was for hardcore pornography. But the idea here is that it's something that's very, very hard to explain what is it that I'm looking for. But if you give me an example, it's very easy for me to say if it is or not what I'm looking for. Okay, so this kind of I know it when I see it applies to many, many different use cases. And neither supervised nor unsupervised approaches are well suited for solving this problem. And so what we argue is that you need something between the two things, which is called in general interactive learning, where you have a feedback loop. So there's an ongoing loop here. The machine does something, then it passes over to the human, which does something else, and it passes feedback back to the machine and iterates over and over. So two examples of these things, to make things a bit more concrete maybe, is things we have worked on this slide. So the first one is e-discovery. We try to summarize this in the legal system, especially in the US. What happens if company A sues company B because they think there's patent infringement or something? Together with the judge, they agree on a set of documents company B has to provide to the accuser, company A. And now it's up to company A to dig into these documents to find out the smoking gun, right? So the email to the CEO who says that company B was aware of whatever. So this process is called e-discovery. Xerox, our previous employer, they still have a whole department of these things. A second similar topic is sensitivity review. You might have followed the release of the John F. Kennedy's assassination data. This happens all the time, right? So government, by law, many governments have to release public records after X years. And there is a set of instructions that the reviewers have why they can avoid one document to be released, or they can redact it, right? So redact meaning taking out some names or something like this. This might be because the person's alive, because there is some diplomatic relationship which could be endangered, etc., etc. These instructions are over-specified, hard to formalize, and then people have to look into these things and have to understand it. So it's a very similar process to e-discovery. One set of tools which is very popular for this interactive learning, and I think it's the one which has shown most success, it's called active learning. Again, I assume that many of you are familiar with it. The idea here is that you give the machine the possibility of the initiative. So now you have your algorithm running, and someone says, wait, stop here, let me use an additional resource, which is a human, and let's ask the human what the human thinks about this specific data point. And the idea that the way that it selects this data point will help minimize its uncertainty or something similar. So you many times get these kinds of curves. This is for the identity recognition, a structure prediction problem. And then what you have is here you have the number of labeled instances, and here you have the way that you indicate success, which is called the F1 measure in this case. And what happens if you just pick up a random set of data points, you see with the blue line here, and then if you let the computer, the algorithm, to choose to pick up which data points it wants to select, you get the green line. So this kind of conclusion is generic in active learning. What it says that if you let the computer pick up its data points, then with 30 instances you get as good a performance as with 150 data points random selected. So you reduce a lot the amount of annotation you need. Now the assumption here is that the human will provide a feedback which is the same that the human is using to learn. Right, the same in the initial annotation. This might not be always the best thing to do, and there have been studies, in particular in document classification, which says that annotating a whole document with a label, the reading the whole thing, it takes 3 to 5 times more than just annotating a single word. Just saying, look, I know that football is something which, or ball is something which is related to sports, or that software is something related to IT class, okay? So this kind of feature labeling is much easier for humans to do, but there are many problems. One is that the type of this feedback is different than the type of the annotation that the computer has to provide. So how do you incorporate this into the algorithms? It's not trivial. There are solutions, but it's not trivial. And the other one is that the information load of a single feature labeled can be very small. So how do you propagate it towards similar features? And finally, this is a very standard problem in anything related to natural language processing, is you have this ambiguity of language where one word might mean different things depending on the context. Bank, again, is a kind of an example. It might be a geographical feature, it might be a financial institution. I'm mentioning this because we have been revisiting this over the last years in something which is in our current interest, tackling these 3 problems. Okay, so this is what basically I wanted to share. So my message here is don't be prisoners of your performance indicator, even assume that you have only one, right? I know that in real applications you have many, you don't only have accuracy, but you have speed, you have technical depth, you have a number of different things. But even if you have only one, ask yourself, does this really capture success for the human? A good way of looking at this is, does this correlate with human judgment? With what humans judge to be good, right? And then the second thing is, maybe there's some part of it which is very hard for the human to do, but very easy very hard for the machine, but very easy for the human. There's some kind of feedback loops that you can incorporate which could bootstrap your algorithm. And once you are there, you can start looking into the parts which are difficult for the subparts which are difficult for the humans, and try to automate them. And then this opens many interesting research directions, because you start being into this intersection. So if you're interested in these things, our center has a blog, and this is something close to the heart of my team. So we publish a few non-necessarily very technical blog posts about this topic. And these are the people who work mostly on these things and who are behind many of the conversation which nurtured this topic. So I'm finishing with this. Thank you very much.
Okay, some questions. Yes.
You started out with Kasparov and the idea of the computers and the people together doing chess. It's something that's come out of that. I have a question to you related to that. You didn't mention it. If a game is solved in AI, basically closed, and the AI can always solve the game, there isn't any benefit to the human plus the computer in competition with that game, is there? And then the second thing would be, very recently, AlphaGo went from AlphaGo to AlphaGo 0, which then can now presumably beat all computer models in that game, as well as all experts. In that scenario, is there any advantage for a computer plus human competitor in that? And if we look a little bit beyond that, some of the talk recently in AI has been that we're really looking at augmenting human performance. And they always give the example of Kasparov and the computers plus, a chess game of computer plus humans. But what we're seeing already is game theory with AI applied that are showing that the computers alone, if it's a solve game, or if it's, in the case of AlphaGo 0, asymptotically, or just basically win, period, without the human input.
So the first question, checkers is a solved problem, right? So from the definition you can now. And I think the question is, what is the goal of a game, right? So the goal of a game is to learn for humans, or to entertain, or whatever. The fact that we use this as a benchmark for machine intelligence is because it's easy to formalize, because you have a very restricted set of actions that you can perform, much as in the real world. And so I say what everybody else says, we should take these successes, which are impressive, with a peak of caution, with a bit of caution. They don't say anything about intrinsic machine intelligence. They're just good examples. The same thing with synthetic data, which is becoming popular again in natural language processing. We should see this as test beds for our algorithms in order to see what they can add. So in AlphaGo 0, that a new way of a new reinforcement learning algorithm, which is interesting, that introduces this idea of autoplay, which is becoming more and more popular. So these kind of things are important, not I think the final game itself. Something trying to be related is that in industrial robotics, a hot topic these days is what's called cobotics. So this idea that you have a human and a robot doing a shared task, and the robot is not in a cage, which is normally the cage being a separated physical environment from the human, which is normally the case in industrial robots. And I think that is much more interesting, because you have this idea that there are some things which a human does better, or something which a machine does better. So let's try to combine these two things. And so I wouldn't read too much into the successes in games in general. The truth is not that question. We can avoid it.
Do we have any good examples of reinforcement learning applied to NLP, NLG?
So we are working on reinforcement learning for NLG specifically,
Well,
but we're working on it. So it's not something. So it seems like NLG is a good example where you should be able to apply these things, because it's a sequential decision-making problem. So as you go, you have to start producing more and more words. But you can only know at the end if you did it correctly, especially in German languages like German, where you have the important part at the end. So you have to wait until the end to say if it's good or not good. And reinforcement learning is just a way of assigning credit to in which part of your step you did the wrong decision, you should go back. It seems like it could be a good test bed, but for the moment, I mean, there are some, in the academic benchmark, there are some good successes using LSTM, this was mentioned before, but in real systems, rule-based systems still wrong, right? For NLG specifically.
I think this is our last question, and after that we have to do a wrap.
Hi. We often hear that the future of AI might be in unsupervised learning. Maybe you heard that. What would you think about that?
I guess you're talking about the cake story, about the cake talks. Yeah. Well, I mean, it seems obvious, right? So with supervision alone, you can't. I mean, everybody who has worked on these things, and I think many people here did from my conversation with you. You do it for one domain. You move slightly bit the domain. You lose slightly bit the provider of the data. So we have worked with information extraction for hospitals, and it's the same domain, it's the same type of things, but one hospital expresses itself differently from another hospital because people are different, and your algorithm reduces it. There's been very interesting studies in, I think, 2014, which reduces up to 10% of your accuracy, just changing the person who's producing the text. And the current way of solving this, and of the excuses of machine learning people is, well, I need more training data. So I think unsupervised is a great way. That's how human learns. They look around and they start figuring out things. And I think what's called distance supervision, weakly supervised, might be a very good starting point for these things. So you have one good method, and then you want to apply it, and you use this kind of distance supervision or weakly supervision in order to steer it towards the other direction. I think there are much more low-hanging fruits in this part than in unsupervised. But it's very application dependent too.
So if everyone can help me thank you again for this wonderful speech. And so now I'd like to remind everyone that the keynote speech is about to start at 1 o'clock.